All right. So even though we talk a little bit about symmetry and we talk about the different infrared reactions, this is also going to be a section with more vocabulary in it, maybe things you've not heard before. So here we're talking about metal carbonyl complexes, and they have a general formula of your M is your metal, and then what's a carbonyl group?
The C double bond into an O.
Nope, that's a carboxyl.
Oh, okay. Carbonyl.
Mm-hmm. It's just a CO group.
Oh, okay.
So
no double bond.
Yep. So you can see this one has 5 carbonyl groups and then a chlorine. And so then of course you'll have your 6 minus N carbonyl groups and N other groups. So it's like 6 minus N. I could have MCO6, but since I have MCO and then I have chlorine, that's an N of 1. So chlorine is N equals 1. So that'll be metal CO5 Cl. In this case, it's manganese. Now, so when you actually submit these to infrared spectroscopy, now you can actually get a number of readings. And so you can get more information about the molecule based off the actual, the individual infrared absorptions. So in here you can get carbonyl stretching modes. So just the COs on the end are going to be stretching. You can get metal carbon stretching modes, MCO deformations, and carbon metal carbon deformations. For this in particular one here, you'll find that it has a single IR absorption of about 2,000 wave numbers. And so one thing you'll notice is if we go all the way to CO6, that's an OH point group. Your higher symmetries are actually going to start to kill off your IR absorptions, and it can make things a little bit harder to read. One thing we can do is we can start comparing these. In the textbook, you'll find there's sulfur hexafluoride that also forms an octahedral structure. So you can start comparing these to the infrared activity of sulfur hexafluoride. And oftentimes that's what you'll do is you'll compare your readings to a simpler molecule, and you'll just start to pick things apart that way. We can use group theory to talk about the IR absorptions. Oh, so let's see. So this here is of course the C4V. And at some point, maybe sit down and go through the point group assignment and see if you can figure out why it's a C4V. I mean, of course, you can see the C4 axis. However, there are no C2, like, you see how just putting that chlorine in there takes away the perpendicular C2 axes?
Mm-hmm. Yeah.
So stuff like that. So on this table here, what are my 2 symmetries for that with possible infrared activity?
A1 and B2. Wait.
Nope, A1 is one of them.
Oh, sorry. And then E.
E, yep.
Okay, what's the left and right column again for the ones that don't have thick captions at the top?
Oh, well, it's really just telling you. So your first column is rotations and translations, X, Y, Z, and then your rotations. And then your far right column, your combinations, that's going to be your Raman activity.
Okay, that's Raman. All right. And then, okay.
Now, I know up here I said there was 1, and down here I said there were 3 infrared absorptions. And this is why some of these complexes are harder to take apart. There's 1 carbonyl stretch infrared absorption. There are 2 others that are different stretches or deformations. And so, of course, here, your A1 and your E denoting those the infrared activity there. Now, this one here, I kind of wanted this one just to be more of a vocabulary thing. So here's another way to denote a molecule. FAC, then you have chromium CO3 NH3. So your your NH3, those are amine groups. Then you'll have your 3 carbonyl groups, and this is called a facial structure. Your facial structure, so what you're imagining is 3 ligands that are the same occupy the 3 points of a triangle.
Yeah, so there'll be like 3 on top that are the CO3s, and then just the CO, sorry, and then the NH3s will be the 3 on the bottom. Is that what that means?
Well, let's draw it. Let's see what we can, let's see if you got it. Because the way I'm looking at it, yes, but I want to know what you mean by that.
Oh my gosh.
Have you looked at this kind of terminology in organic yet?
No, I've never seen the facial, but
By the time you're done with these 2 classes, you're going to be able to read a lot of articles and now understand what the different terminology means.
yeah, definitely. Okay, this is what I drew. It's kind of
Yep, that's actually it. Yes.
Okay.
So the way I drew it is, we'll say, put chromium there. Oh, this is going to be an octahedral, but up here we have an amine group, and then back there, carbonyl, carbonyl.
oh, I drew double bonds. I keep wanting to do that. Oopsie.
So this is the way I did it, which is the same idea you have. You've just rotated yours,
Yeah.
so that you have one triangle up, one triangle down. Another way you could look at it is, so let's say we could do that. So we're drawing a staggered configuration. So that's another way you could look at it. Now, this one has a point group of C3V. Let's go back up. I know we have that table on here somewhere. Here. Now, here's where it starts to become confusing, and this is why we want to go to this kind of next level. So here you can see that you have 2 symmetries that are marked as IR active possible. In the lab, this one, however, will only give you 2 infrared peaks, not the full 3 like you would expect. So now, granted, there's 2. You could say there's 2 symmetries, and so the 2 IR peaks make sense because there's only 2 symmetries that are denoted as IR active. But it still stands to reason, like, well, if that's true, then why does ammonia, which is also a C3V, have 4 infrared peaks? So we have to kind of make it a little bit more difficult to really try to figure that out. Okay. So let's start trying to figure that out. First, I wanted you to do this. This is essentially what we just did above. See if you can figure out why it's, and I shouldn't have told you it's C3V,
That's okay.
but see if you can follow this. When you drew it, this is essentially how you drew it right here.
Okay, I see, but why no horizontal mirror plane?
Because you remember your principal axis,
Oh, wait, I get it. Never mind, never mind.
your principal
Sorry.
axis has to be there.
Silly question, actually.
No, it's okay. You're just learning symmetry. Some people, this takes years of study to master. So give yourself the room to do it. So you always remember your horizontal axis has to be perpendicular to the principal rotation axis.
Yeah.
So it's not linear. It does have a CN axis, a C3. Are there C2 axes perpendicular? Nope. Is there a horizontal mirror plane? Nope. Are there vertical mirror planes? Yep, C3B.
Word.
Okay, so now we have to start asking, well, how can we actually get a better bead on what the infrared vibrations are going to be? Okay, well, we need to figure out how many irreducible representations each symmetry on there is going to give us. So we have A1, A2, and E, all right? So the number of irreducible representations is going to be 1 over H, which is the order. And then the sum, so I just use Greek letter zeta.
Zeta.
So zeta is going to be the coefficient of the individual symmetry operations. I like this one because you see the coefficient for E is 1, for C3 is 2, and sigma V is 3. Okay. Then chi is going to be the character of your overall irreducible representation, and chi sub r is going to be the character of the reducible representation. So it's like in your A1, your chi r's are 1, 1, and 1. But we have to know what gamma is, the reducible representation.
Okay. Chi gamma is reducible, chi r is irreducible. And then the zeta, remind me.
Those are those coefficients in front of your symmetry operations. This one is confusing the first couple of times you calculate it. But if you start taking molecules and you see how many infrared absorptions they have, and you just start taking the character tables apart, this is something that eventually becomes secondary. You would do this a lot experimentally in a spectroscopy lab. This would all be part of your analysis. What am I seeing? Okay. Now, so the first, this is not the best way to put it, but we're going to look for two different types of reducible representations that will form our overall reducible representation. So gamma UMA will be the number of unmoved atoms for each symmetry operation. And then the coordinate contribution from each symmetry operation. That one is easier than it seems. So let's go ahead. I wonder if I can. Let me copy this. So I can move this down. Oh, it did. Look at that.
Thanks.
Okay, so I'm going to draw my ammonia. And I picked this one just so we could have a little bit of a challenge. You can see how this works before having you do a more straightforward one. Okay, so what we want to think about is our coordinate axes on each atom. Okay, so let's start looking for our gamma for unmoved atoms. Okay, so for E, how many unmoved atoms do I have?
For E, how many unmoved atoms do I have?
Mhm.
Let's see. So is it just 2 for the E? Because
No, so your symmetry E. Your symmetry operation, not your symmetry grouping.
So is it just 1 then for the
So E is what? Symmetry operation.
identity?
Identity. And how many atoms do I have there?
3, 4.
4. And how many don't move in identity?
None of them move.
So that's 4.
Oh, okay.
Now, and I put the axes on there. You can start to think of this either in terms of individual atoms or the coordinate axes, what happens to them. Okay, so your C3 operation, how many atoms don't move?
C3. That's just the 1, just the nitrogen.
Yeah, so 1. And what about a sigma V? How many atoms do not move?
Sigma V. 2, the nitrogen and whichever hydrogen, right?
Mm-hmm. So 2. All righty. Now, the gamma XYZ, coordinate contribution. Okay, so here's how we can look at this. Each one of those inputs in the gamma XYZ is going to be the trace of the symmetry operation matrix. Do you remember how to do that?
The trace of it? No, not really.
Okay, the trace is going to be down the diagonal. 1 plus 1 plus 1. The trace of E is 3. So that's the first element of that gamma. Okay. Now, not. I'm sorry, but I wanted to really finish this today, but I was like, I don't really want to leave finding these vibrations as kind of an abstract idea.
No, that's okay.
So I was like, let's just go ahead and do the hard part so we can see how we can calculate this. Because if you look at, and I picked this also because in the textbook, she tells you that ammonia has 4 specific infrared vibrations. Great. Why does one C3V have 4 and another one has 2? Okay, well, you can figure that out with group theory. So let's now, and I like this one because now our C3 matrix I picked it because now this doesn't seem wholly intuitive.
Sure.
What is the trace of the C3 matrix?
2 cosine of theta plus 1.
But we need a character in there for a C3 operation. What is theta?
120 degrees.
120 degrees. And when you do that, it's going to give you a character of 0. So yeah, we just do cosine of theta plus cosine of theta plus 1. We get the 2 cosine of theta plus 1, put in the 120, and we end up with a 0 for the character. Let's look at sigma V. And this is why it's great that these, actually, all of your mirror planes are going to come out this way. It doesn't matter which one you put in here. What is the trace of my sigma V?
Just one.
One. So all of your mirror planes are going to come out as one. So you can remember that and use that as part of your gamma XYZ. But because you notice they're all going to have, the traces are all going to have two ones and a minus one. It just depends on where the minus one is at. All right, now the gamma for the equation up here, that gamma there. So that's going to be our gamma 3n, okay? And do you remember what 3n is?
That's the coefficients in front of them. Wait,
No, so 3n, remember, is your total degrees of freedom.
total degrees of freedom.
So that's going to include translation, rotation, and vibration. 3n is total degrees of freedom. That's why when we, for like a nonlinear molecule 3n minus 6 are your degrees of vibrational freedom.
Okay.
Okay, the way we get this is gamma UMA times gamma XYZ. So,
You do that as a matrix?
um,
Do we just
this I need to look up the name. This has a specific name. It's a specific type of multiplication from linear algebra. But the way we can do that is we have 4 times 3, 1 times 0, 2 times 1.
Okay.
So that's going to give us 12, 0, 2. That is our gamma 3n. Now, we look at this equation. So now we have all of our chi gammas. Each symmetry element, each symmetry group is going to give us a gamma r, and our zetas are going to be the coefficients of those. And so then, of course, our order is 6. Okay, so how many of, now the question is, how many of each one of those symmetry groups are we going to get from this reducible representation? Okay, so the number of A1s is going to be 1 over 6. Okay, so in front of the E, there's 1. The character from the gamma 3n, 12, and the character from A1 is 1. All right. Do I need to bring the character table down again so you can see it, or?
Maybe.
Yeah, let's do that. Okay, so you see there's a 1. There's a 1 there, which corresponds to our first one. And then we have our 12, and then A1 gives us a 1 in that first position. So then the 0 will match up to the second position, the 2 will match up to the third position. So then that's going to give us, okay, so 2, 0, 1, and then 3, 2, 1. So 3 and then over to, so like that last one, 3 in front of the sigma V, over to the gamma 3n, which is a character of 2, and then back over to the character table. So the last character of A1 is a 1. So it's 3 times 2 times 1. And when we multiply this up and divide by 6, you're going to get a total of 3 A1s. So let's look at the number of A2s. 1/6. All right. So again, in front of E, there's a 1. From gamma 3N, there's a 12. And then from A2, there's a 1. Let's see. 2 in front of C3. 0 from gamma 3N. And then 1 from the character from A2 plus 3 in front of sigma V, 2 from gamma 3N, and a -1 from the character table. This gives us 1 A2. Now keep in mind, since we're getting these from gamma 3N, these are the number of each symmetry group we're going to get for everything. And that's going to be translations, rotations, and vibrations. So then we'll have to reduce this a little further just to figure out how many of these represent our vibrations. So now the N for our E symmetry group, number 6. Okay, so from in front of the E column, there's a 1, 12 from the gamma 3N, and a character of 2 from the E row. Plus, let's see, 2 from in front of the C3, 0 from the gamma 3N, and a -1 from the E row. And then 3 from in front of the sigma V, 2 from the gamma 3N, and 0 from the character table in the E row. When you multiply this up, you're going to get 4 E's. Now, the way you write this is your total gamma, which started out as 1202, has now been calculated to show you that you get 3 A1s plus an A2 plus 4 E's. Okay, now we want to turn this into our gamma for vibration. So what we're going to do, the gamma minus translational gamma minus rotational gamma. Okay, so that's going to be 3, 1 plus A2 plus 4E, the gamma we just calculated. Now, let's think about gamma of translation. What groups up there? So I want you to try to, even if you just have to give it your best guess. Which symmetry groups up there represent translation? Translation, remember, is in a single dimension. So it can move. What are the 3 dimensions a molecule can move in?
The 3 dimensions, like the XYZ.
Mm-hmm. So which symmetry groups represent those translations?
Is it the same ones that are IR active?
Yeah, so it's your A1 and your E. So we're going to subtract off A1 and an E. Now, which symmetry groups give us rotation?
I guess the A2 then.
A2?
And wait. A2 and E.
A2 and E. We're going to subtract off an A2 and an E. So our gamma vibration, is going to be 2 A1s plus 2 E's. And how many vibrations does this give us?
Vibrations. It's just the 2. Wait. Because identity doesn't move, right?
Well, you don't make it too hard. Just look at what's right there. How many vibrations does this give us?
4.
4. 4 vibrations, which corresponds to the 4 infrared peaks that ammonia shows in experiment. So this is the longer, more exact way to get at this. But if you can start to take all molecules apart like this, you're actually going to be able to calculate the infrared vibrations that you're going to find in labs. So you run your experiment, you get your peaks, and then you can compare it to stuff like this, and you can start to get a better picture of what's going on inside the molecule. So this is a longer process, but it's an important part of the group theory. And you see the math isn't that hard. It's just trying to keep track of what you're doing.
Yeah.
So if you look in the textbook, go to the part of the chapter where she's talking about ammonia and compare it to this. And so you remember, because we did it in class and we showed those different stretching modes and deformation modes. And so if you compare those stretching and deformation modes, knowing that those are the four that are going to shift the electric dipole and cause infrared activity, you now have calculated the four that you should get, and you notice that those four correspond to the two symmetry groups that denote infrared activity. So now it all kind of fits together. Okay. So I gave you water to work on. A little more straightforward. Because you don't have that crazy rotation matrix. Do you remember, did we go over what a C2 matrix is?
Perchance. I mean, maybe.
So the others you should have. I'll give you C2. So there's your C2. And this just illustrates what I said before. You should be able to figure this out just because it's a mirror plane. So your sigma v prime, the -1 just switches positions. The other two you should remember. So with those two matrices, see if you can get this. Character table is a little difficult because I got everything out of line, but you still get the idea. Trying to remember off the top of my head, when we do that multiplication of gamma UMA and gamma XYZ, I think in group theory, it's called the inner product. I'd have to look it up to be sure by the way you can represent it. Just like that.
Oh, okay, question.
Mhm.
So I'm to the part where I'm doing my, oh wait, no, I have to do a different one. Okay, never mind. Oopsie. I understand.
So yeah, just trying to remember from a few years ago, I think that's the inner product of the two reducible representations. Every area of math has its own kind of products.
Is NE3? Am I on the right track?
The what?
NE?
Oh, well, you should be getting in for A1, A2, B1, and B2.
Oopsie.
You went down the column instead of across the. So
Right, that would be A1, right? A1 would be. I just wrote it as.
Oh yes, it'd be three A1s.
Okay.
Weird.
I get it.
You know, I did notice this before, but you could actually go down. It's not the proper way to do it, but if you look down the columns, it matches the rows.
Huh.
One ones, one minus one minus one.
Oh, it really.
One minus one minus one.
Oh, it would have been totally fine then.
You would have been. It just wouldn't have been the proper way to do it.
2. I got 1.
Yes.
Yeah.
All of this to figure out how many infrared vibrations will water give us.
Yeah, I want to know.
We already know for a fact that the symmetric stretch is not one of them. So there's other vibrations occurring, but just not IR active.
Yeah, this really isn't that hard. It's just a lot of writing, a lot of keeping track of things.
Mm-hmm. Yeah, once you start to get used to linear algebra and group theory and matrix math, the operations themselves are easy, but there's a lot to keep track of, knowing what do I multiply to what, because there's new rules.
Oh no, I didn't get an integer for B2. What did I do wrong?
Well, try to finish it by using 2B2, and then we'll go through the whole thing.
2B2?
Yeah.
Okay, now I got a whole number.
There you go.
Yay. Is that just something you just gotta do if you get a weird number, or?
Well, yeah, you should always look at, these should always come out to be a whole number.
Mm.
So if you don't get one, see if you can figure out where it happened.
I also got 3 for that one.
For B2,
Me too.
Mm.
Oh,
You-
did I do it wrong?
you have 3 B1s.
I also, yeah, I have 3 B1s. Maybe I just algebraed wrong.
It's possible.
Okay, I guess I don't know what I did wrong.
Well, when we go through it, let's see if you can figure it out.
And then,
So your total gamma should be 3 A1s and A2, 3 B1s and 2 B2s.
2 B2s.
And then you've got to take off the translation and the rotation.
Just this. Yeah.
I'm going to start working through this because I want to make sure we cover the last few slides. Because you'll see it in organic chemistry, but I want to talk about chirality. All right, so for gamma UMA, so for E, it's 3. For C2, it's 1. For sigma V, it's 3. And for sigma V prime, it's 1. Did you get that one?
Yeah.
Okay. Gamma XYZ. Of course, remember from above that for E, it's 3. For our C2, it's a -1. And for each sigma V, it's going to be 1. Okay, so then our gamma is going to be 9, -1, 3, 1. Okay, so now let's, and of course, again, this is what our UMA times XYZ. Okay, so let's start number of A1s. The order is 4, so it's 1/4. And we should get, so for this one, so the coefficient in front of each symmetry operation is 1. So for you get 1, 9, 1. If you compare this to the character table, I see 1, -1, 1, 1, 3, 1, and 1, 1, 1. This is going to give me 3 A1s. So I should get 12 in there, and I divide by 4. Number of A2s. 4, 1, 9, 1. And again, if you ever need to just back up and look what we did before to go slower through this, but you seem to be doing okay. -1, 1, 1, 3, 1. No, hang on. That's a -1. A2. -1. There we go. plus 1, 1, minus 1. This gives me 1, A2. My number of P1s, 1/4, 191, 1, -1, -1, 1, 3, 1, 1, 1, -1. This will give me 3 P1s. And then my B2s. 191. 1, -1, -1. 1, 3, -1. 1, 1, 1. And so there you see you get 9 plus 1, which is 10, minus 3, which is 7, plus 1, which is 8, divided by 4.
Oh, I did wrong.
2 E2s. Okay, so my total gamma, 3 A1s plus an A2, 3 B2s, or B1s, and 2 B2s. Again, with vibration. Now I'm going to subtract off the translation, which is going to be A1, B1, B2. And then subtract off the rotation, A2, B1, B2. This gives me a vibrational gamma of 2 A1 plus B1, which gives us our 3 IR active vibrations of water. So kind of a long process, but it does help.
Yeah.
Okay, now chiral species. Want to make sure you have an idea of chirality. Chirality are non-superimposable mirror images. So if you look at the mirror images, there's not actually a symmetry operation you can perform that will make those superimposable. And also chiral molecules lack improper rotation axes. Okay. So can you see how no matter what you do to one of those, it's not going to fit on the top of the other one?
Yeah, I see.
So again, if you try to rotate them over on all of your different colors point different directions, you can get close, but never exact. Can get harder here. Here's some fun names. Lambda tris oxalato iron 3 and delta tris oxalato iron 3. Okay. Lambda and delta. Lambda is a left-handed or anti-clockwise helical twist.
Mm.
So this one, it's not really, you're going to have a counterclockwise C3, but you notice how the molecule itself is kind of a twisted helix.
Yeah, I see it.
Okay, so your delta is a right-handed or clockwise helical twist. So you can kind of see the two differences. And believe it or not, these two are chiral. If you try to rotate them and put them on top of each other, so like what you would get is this up oxygen here would end up over here, but it would be up. Mm-hmm. So they're just not going to match.
Yeah.
So let's see, what are some of these? Tris. 3 identical, often complex structural groups. That's part of the name. Oxalato. In this case, it's 3. It's 3 oxalate groups, which are bidentate to the central iron atom. There's a new word for you, bidentate. What do you think that means just by looking at it?
I mean, just they both. I don't know. I mean, I can see what it means.
So
but-
bidentate, tridentate. You have basically imagine, so you have your oxalate group coming in, those two oxygens reach out and they both think of it as both of them kind of grabbing the iron. So that's bidentate.
Okay.
And so it's just basically you
There's
get
two connections.
yeah.
In the center.
Yep. And so then, of course, we talked about this earlier for this molecule. It has a hapticity of 2. So remember, and this is due to the bidentate coordination of the oxalate ions. So your C2O4s. And so remember, your hapticity is the number of contiguous atoms in a ligand directly bonded to a central metal atom. So you notice how the oxygen goes to carbon, carbon to oxygen. That's contiguous. And so you have that 2 bonds to the metal atom in the center. That's a hapticity of 2. So, and you can look up all of these different things, but I wanted you to see how deep some of the naming can go. So again, remember your lambda is a left-handed anti-clockwise or anti-clockwise helical twist. Delta is a right-handed or clockwise helical twist. And
How do you assign like priority for that?
Priority?
Well, like with chiral things, like you have one of them is the most important based off of molar mass, and then you go counterclockwise or clockwise. Like, how do you do that with this to decide if it's left-handed or right-handed?
Oh, for this one, if it's left-handed or right-handed, you really want to look at because the molecule itself provides the helical twist just based on its shape. For this one, it's much easier. You say, well, that one's going to have to twist left-handed. This one's going to have to twist right-handed.
Okay.
So that makes your lambda and delta configurations. Well, let's see. I guess I see what you're saying here.
Like, there's probably a rule for it out there, right?
Let me look that up. I didn't think about that question.
Yeah, I don't know.
I've gotten used to looking at these over the years, and so I could see it, but I didn't think about that as a question.
Well, I mean, they talk about the structure of DNA, and it has like a particular handedness. So I've always.
Okay, you know the definitions now. Let me try to figure out how we know which rotation is principal.
Okay, word. Yay. Are we doing a different chapter on Wednesday or?
Yep.
Okay.
If we are done with this chapter.